welcome you all. Today is the 8th lecture in the series on marine hydrodynamics, and in the last few classes we have already discussed basically the conservation laws. One is the conservation of mass, the second law is the conservation of momentum, and then we talked about application of this equation of motion, what is the conservation of mass, and the continuity equation, which is nothing but the law of conservation of mass. And then we have talked about several applications. With this background, today we can talk about areas two dimensional flows, because we have already talked about velocity, potential, stream functions. So, easily with this understanding we can talk about two dimensional flow. So, the question comes, why two dimensional flows? Because everything in nature is three dimensional, but why we are thinking of two dimensional flows? Another obvious question comes, and when can we consider assume that the flow is two dimensional and still we get accurate realization of the physical model that is under our disposal. One of the fact, suppose because we are looking at a flow problems, if the component of velocity in the z axis, suppose it is negligible compared to the component of velocity and other characteristics, motion characteristics in the x and y directions, then you can always neglect the z component and consider the flow as a two dimensional. In such situations, because the z component we are neglecting, we can always call, because in the Cartesian coordinate or in the polar cylindrical polar coordinate, always let us say Cartesian coordinate, here always we can say that the flow is a function of x and y and is independent of z, and in the process we consider the flow as two dimensional. So, only emphasis will be giving on the x and y component of the flow, and z component is negligible compared to the x and y component. Another aspect is that, suppose I have a situation where to analyze instead of analyzing a three dimensional flow, I still can consider a two dimensional flow if suppose in the xy plane the flow is symmetric and I took any plane, and each of these, suppose I say z is equal to 0, z is equal to 1, z is equal to 2, any of these plane, if I say the flow is symmetric in nature. So, if flow is symmetric in nature, then I can always ignore the z component and I analyze the problem in the x and y components, particularly in two dimension, and generalize it, assume that the pattern remains similar in nature in the z direction. In such a situation also, we do say that it becomes easy to analyze the problems in two dimension. The advantages are many of this two dimensional flow of a three dimensional situation, because we are reducing the dimension of the whole problem by one means, both theoretical and computational efforts we are reducing to a great extent. And in fact, once we consider the flow as a two dimensional, because we can think of functions of complex variable where we write at every point z in terms of in the Cartesian coordinate as a point in the real plane x and y in terms of x and y, or in terms of r and theta in the cylindrical coordinate. So, because of this, even if to analyze two dimensional flow problems, we can take the help of complex function theory. So, today let us give emphasis how the complex function theory we can take into account and then analyze flow problems in two dimensional. So, now we will start with a very simple example, or before going to that, let me say what I mean in the complex function theory and how I will relate a two dimensional flow to a complex function theory, to the complex function theory. So, suppose I know that I have the velocity potential phi and the streamlines rather the stream function psi. Phi is the velocity potential and psi is my stream function. And we know if the flow is rotational in nature, particularly when the fluid is incompressible and the flow is rotational, we have seen that phi x is equal to psi y in 2 dimension and phi y is minus I x. So, this is what we say the Cauchy-Riemann equations. We have already talked about it. I am not going to the details. Cauchy-Riemann equations. And then, so from the theory of complex function, if I look at a function w z which is written as a function of phi plus I psi, where phi is the velocity potential, psi is the stream function. Here we have both phi and psi are function of x and y. They are associated with the flow, where phi is called the velocity potential and psi is called the stream function. Now, if I put w z is phi plus I psi, then what will happen, where again z is x plus I y. If I have z is x plus I y, w z is phi plus I psi, what will happen if you del x? If I say del y tends to 0, what will happen to dw by dz? This I can always write a limit, because my del y tends to 0, I can call it a del x tends to 0, del phi plus I del psi by del x, and which always I can write limit del x tends to 0 which I call it del x tends to 0 del phi by del x plus limit del x tends to 0 del psi by I times del psi by del x, and del phi by this becomes del phi by del x plus I del psi by del x. So, this phi x is nothing but u, and psi x is minus phi y, and that is minus I into v. Here I square is minus 1, that is the complex number from the theory of complex numbers. So, what we have seen that in a similar manner, if I will say del x tends to 0, then also I can easily derive that dw by dz is equal to u minus iv. So, unlike here del phi by del x, it will come del phi by del y, and from there I can easily get that. Now, what will happen, because now, so in the process I have brought in a function w, and this is a complex function of phi plus I psi. Now, we know from the theory of complex numbers that if wz is phi plus I psi and it satisfies the Cauchy-Riemann equations, then wz is, we say this is analytic. Of course, here I assume that the functions are differentiable, so they are continuous. Once we say the functions are differentiable, because we are looking at both phi and psi, they are irrotational associated with the flow which is inviscid, incompressible and irrotational, and in the process both phi and psi satisfy Laplace equations, and as a result both phi and psi are continuous. So, I can always say that wz is an analytic function. This is one of the major thing of introducing, and this wz I call the complex velocity potential. Now, with this understanding, now if I will come back to work out few examples from which it will be very clear what exactly how this W is representing the, how they are associated with the flow, So, and how will you understand that this is a flow of a particular type or particular nature. So, now let us say W z is equal to z square. We will emphasize today on various examples. So, if W z is z square, then what will happen? Then W is equal to W z is equal to phi, I can write that phi x y plus I psi x y, and this will give us x square minus y square, because I am putting plus 2 I x y, because I am putting z is equal to x plus I y. Once this is there, then what will happen? My phi x y is x square minus y square, and my psi x y is equal to 2 x y. So, the equipotentials, if phi is equal to constant, if this is constant, I get the equipotential, and if I say this is equal to constant, I get the streamlines. So, this will give me the streamlines, and this will give me the equipotentials. Now, let me draw it. Suppose I take the xy plane, and what will happen? My psi xy is constant, and I can always say that y is equal to, from this I can get y is equal to 1 by x. I always can get the flow in this way. Depending on the constant is positive or negative, my flow can be in this way. On the other hand, if I take, these are my streamlines. Now, if I say x square minus y square is a constant, I can have flow like this. And here also I can have. Similarly, in this axis also I can have. So, flow can either in this way or in this way also it can flow, and we can easily see that they are confocal hyperbolas, and here in case of the streamlines, the lines y is equal to 0 or x is equal to 0, they are the asymptotes. Asymptotes in this case. On the other hand, in this case, what will happen to the line y is equal to x? If I look at the line y is equal to plus minus x, then in this case, in the case of equipotential, they are the asymptotes. The another point is here. What happened at 0? At 0, if you look at 0, dw by dz is 0 at z is equal to 0. So, that means x y is 0. Here dw by dz is 0, and once dw by dz is 0, here I will mention, I call this as point, this 0 0, because this is 0. So, I call this as my u component is 0, my v component is 0. So, I call this as a stagnation point. So, 0 0, this origin is a stagnation point. So, there is no flow across this point. So, the point at which there is no flow is a stagnation point, and in the in terms of the compressive velocity potential, this is, if dw by dz is 0, then I call this as a stagnation point. Now, with this, so this is clear that in this, although we took just a very simple function w is z square, how it can represent the flow, particularly there, how the hyperbolas, the rectangular hyperbolas we are able to draw, and the flow direction is this way. That is the way. Then I will just go to another example, because today we will be spending most of the time on working out several examples to understand the importance of the complex function theory, because this in the early days when there was viscous flows are not well studied, those days by using, particularly when it started with the theory of continuum mechanics, when the potential flow theory was developed, those days the concept of, because those days today's high speed computers are not available, as a result many problems were analyzed by using the function theoretic approach, and those, but it has far reaching effects, because that has given a good understanding about various flow characteristics at in various situations, whether it is flow through a tube or whether it is a flow in a ocean or in a stream or in a channel. So, even if in aerodynamics it has played a very significant role. So, these two dimensional flows. Now, suppose I take W is equal to u z. Here u is a constant, u is a known constant, and z is equal to again x plus I y. So, what will happen? My W is phi plus I psi, and that will be u x plus I times u y. And here another thing I will say, that what is q? The speed. It is nothing but dw by dz modulus. So, and if I say this modulus is the speed, then what will happen in this case? Dw by dz becomes u. I take it u naught to differentiate with the x component of velocity small u. So, q bar is the speed is uniform, the speed is constant, and if you look at psi y, psi x y, here it becomes u naught y, and that is constant. If psi is constant, that means y is constant. So, the lines that is parallel to the x axis will represent the direction of the flow, and here the speed of the flow is always constant, that is u, and we call this is a uniform flow along x axis. Or sometimes we call it the flow is parallel to the x axis, because the streamlines are always lines which are where the constant y becomes a constant. So, the lines which are parallel to the x axis, and they are the. So, and in the process we say W represents the motion of an incompressible uniform flow, uniform stream rather we call it sometimes uniform stream with speed u. Speed u naught, and the stream is parallel to x axis. Basically, I mean the flow is parallel to x axis. I will take another example. Suppose my W is equal to u a square by z. Then as usual my phi plus I psi, I can write it as u a square by x plus I y, and that will give you u a square x by x square plus y square plus I times, rather I will say this is minus I times u a square y by x square plus y square. And if I say that phi is equal to constant, psi is equal to, in this case, minus u a square y by x square plus y square, and if I say this is a constant, that means it will give me x square plus y square is equal to a constant times k times y, and that always gives me x square plus y minus k by 2 square equal to k square. So, depending on the value of constant, k is a constant. So, depending on the value of the constant, and here what will happen, I will get different streamlines. So, and this here I can always see that this will be like this. This is the way the flow will look like. Even if it can circles, all are circles touching the. So, these lines will be the streamlines, and this will give me the potential lines, equipotentials. Equipotential, this is a streamline, then this is again streamline, this is again we will say, these are again this will give me equipotential, this is equipotential lines. Equipotentials, and here we can see that the streamlines touches the, whereas the streamlines they touch the x axis, whereas the equipotential lines they touch the y axis, and they all this. Now, another aspect here is that what will happen to q here. If you look at a w dw by dz modulus, that will give us the speed. Now, I will go to another example here, the third example. The third example, I will take up a line vortices. We have already talked about vortices. Now, let us look at a line vortices in the complex potential, how it will look like. Suppose I say I k by 2 pi log z, then here my z is equal to x plus I y, and if I say phi plus I psi I k by 2 pi log. So, this also I can write it as r e to the power I theta. So, then I can write this as r e to the power I theta, and this is I k by 2 pi into log r plus I times I theta rather. So, which implies I by I k by 2 pi log r minus k by 2 pi into theta. So, here if this is phi plus I psi, my psi will be constant, psi is equal to k by 2 pi log r, and my phi is minus k theta by 2 pi. Now, here again I will see, if I say that this is k by 2 pi log r psi. So, that means if psi is constant, that will give in the streamlines. So, r is equal to constant are the streamlines. So, if r is constant, then I will get various circles. In fact, we have already talked about this in my earlier classes, and then what will happen to the phi is equal to constant, that will be theta is equal to constant. Once theta is equal to constant, the flow is always in the radial directions. These are the equipotentials. So, these are the equipotential, and then the circles centered at origin, that is the, that gives me the streamlines, that is the flow direction. And here again if I look at, I can easily my, since in the from here I can always find what will happen to me if my phi is given by what is del phi by del r. If my del phi by del r, that is the radial component of the velocity, and that will be 0. Here again, what is my tangential component of velocity? That will give me 1 by r del phi by del theta, and that gives me 1 by r del phi by del theta is minus k by 2 pi, and that is gives me minus k by 2 pi r. So, if I said my what are the two things I will look into, these are the two components of the velocity, then what will happen to the my here rather I will consider two separate cases, because if I look at the circulation, case 1, what will happen if I draw a closed curve, that is C, and that is the flow direction, which is because this is the direction in which the fluid is flowing, and this is the point which includes the origin. C includes origin. Then if C is origin is included, then what will happen gamma, because I can always say q bar dot ds, and that will give me, because ds has component. So, if I look at this, then because the flow is in the radial direction, and in the radial direction we do not have q bar is 0, and I have already seen my q theta is 2 pi by r, sorry, minus k by 2 pi r. So, we can always see that this will give us q bar dot ds, that will give me k by 2 pi r d theta, r d theta, that will give me, because x radial, this radial component is 0. So, q theta r d theta, then this will be 0 to 2 pi d theta, and that gives me minus k, because I have taken q theta is minus k by 2 pi r. So, once it is minus k, that means if I look at the circulation, so k is a constant, and this constant is the strength of circulation. And that is k. On the other hand, if I do not include, if origin is not included, then what will be gamma? That means I have to avoid the origin. So, if I have to avoid the origin, then I have to take a small circle around origin, and then I calculate. If I do this, and then I will easily get this gamma as a 0, because I take a small circle. How small the circle is, if it makes a because we have seen here this is independent of r. So, whether how big the circle or how small the circle, it is independent of r, the radius of the circle. So, it will be 2 pi k, k minus k will be, and that will be 0. So, here we see that the streamlines are concentric circles, and here with origin this gives a value k, whereas without origin this gives me the gamma is 0. In fact, in one of my earlier example, I had left this as an exercise, that circulation when you include the origin. We have a similar example. Here we are trying to calculate the flow, and then we had gone to calculate this gamma, particularly the circulation, and we have seen that in both the cases this will be different, and in the earlier case, earlier discussion I have left it. Now, it is very clear that gamma will be different if you include origin or we do not include origin in this case. Now, with this again let us look at a different types of flow. Now, already I know that suppose I take another example. Suppose W is equal to U A Z by a to the power pi by alpha. This is the idea of introducing to various complex velocity potential here is to have a clear cut idea about the various types of flow and how these simple complex functions represents very complicated flow patterns. Now, what will happen dw by dz? If you look at dw by dz, this is ua and into pi by alpha into z by a to the power pi by alpha minus 1, and then we will have 1 a will come 1 by one by a will come by a, and if I say dw by dz is 0, which implies my z to the power pi by alpha minus 1 is equal to 0. There are two cases. If pi by alpha is greater than 1, then z is equal to 0 will represent a stagnation point. Now, if pi by alpha is less than 0, then we can easily say z is equal to infinity only will represent the stagnation point. So, see, even if this is a very little complex, the flow is, but although it depends on a constant, how the flow pattern looks like. Now, I will go to another example. In the next example, basically I often we call this flow past wedge. It will be suppose my Wz is given by C e to the minus I n pi z to the power n plus 1, where my n is alpha by pi minus alpha, and then we put z is equal to r e to the power I theta and w is equal to phi plus I psi. If you do that, and again what will happen to this? So, we can get phi plus I psi equal to C e to the power minus I n pi and z is r e to the power I theta to the power n plus 1, and that gives me C, this is r to the power n plus 1 C r to the power n plus 1 into e to the minus I n pi e to the power I times n plus 1 into theta, that gives me C r to the power n plus 1 e to the power I times theta minus pi into n plus theta. Then our phi will be C r to the power n plus 1 cos theta minus pi plus theta, and my psi will be C r to the power n sin theta minus pi into n plus theta. Now, psi is the stream, this is the stream function. If I say psi is equal to 0, that will give me a streamline, And what happens when psi is equal to 0? Psi is equal to 0 means when r is not equal to 0, that will give me theta minus pi into n plus theta is 0. And if I substitute for, because I have taken my n is equal to alpha by pi minus alpha. So, this is theta minus pi into alpha by pi minus alpha plus theta is equal to 0. So, which gives me, from which I can always get theta minus pi into alpha plus theta into pi minus alpha equal to 0. So, here theta alpha minus theta alpha, this will get cancelled, and then we have pi alpha minus theta. So, that means theta is equal to alpha. So, this is one criteria. Now, the second one, again if theta is equal to 2 pi minus alpha, if theta is 2 pi minus alpha, again we can see that what will happen, psi will also theta is equal to 2 pi minus alpha. Then we can also say that rather we will see that C r to the power n sin, let us say theta is pi minus alpha. So, this is 2 pi minus alpha into minus pi theta minus pi into n plus theta, and this becomes 2 pi minus pi is becomes C r to the power n sin 2 pi minus pi is pi minus alpha into n plus theta, and this is equal to C r to the power n sin. Now, I will put for n is alpha by pi minus alpha by pi minus alpha plus theta, and thus pi minus alpha. So, C r to the power n sin alpha plus theta, and if psi is equal to 0, which gives me obviously that one of the criteria is alpha is minus theta. So, if I plot this, because there are two things I am getting, psi is equal to 0. So, for alpha is equal to theta or alpha is equal to 2 pi minus alpha, I am getting psi is equal to 0. That means that will act as a streamline, and alpha is 0 means theta is alpha. So, if I have any point, this angle is alpha, and then this angle is minus alpha. So, if I have a fluid is flowing, so my fluid will, because this will act as a streamline. So, because of this, because this line is behaves like a streamline, and again I can see that because of my characteristics of W, I can always say that at z is equal to 0, dw by dz will be 0. So, z will act as a stagnation point, z is equal to 0 will act as a, this origin will act as a stagnation point, and this flow is like a, it is a wedge shaped. So, it is showing that as if it is a flow past a wedge, that is why this is represented. Further, if you look at q square is a dw by dz to dw bar by dz bar, and if you simplify this, we can get this as c square n plus 1 square into r to the power n to n, and that will give us q is equal to c into n plus 1 r to the power n. That gives us the speed at which this will give us the speed at distance r from the origin. So, this is a flow past a wedge, this will represent. Now, with this I will now let us look at a uniform flow. We all know that in case of uniform flow, the flow is always parallel to the x axis. If I let us see how we can represent in terms of a complex velocity. Suppose I say I have a uniform flow with velocity u naught. So, if I write as w z is equal to u z, it is very simple. This is can be written as phi plus I psi u x plus I y, and that will give us psi is equal to u y, and if you say this is equal to constant, that will give you the streamlines, that means y is equal to constant, these are the streamlines. So, this is uniform flow, and again it can be easily checked what is dw by dz into dw bar by dz bar, and that is q square, and in this way it is also u square. So, which implies q is equal to u. So, the speed is constant, speed is uniform, u is uniform along the x axis it is, and the fluid is uniform, it is parallel to the x axis, and the speed is also u is equal to u naught if I have taken a u naught. So, this is speed is constant. Now, the same thing if I just twist a little, suppose I say w z is equal to u naught z e to the power minus I alpha, then it can be easily seen that this, if I say this is equal to phi plus I psi, and which is nothing but u naught z is x plus I y into e to the power minus this, we can also write cos alpha minus I sin alpha, and if I put it, then I will easily get my psi as y cos alpha u naught y cos alpha minus this will be I okay y cos alpha, then minus this will be x minus x sin alpha, and that if this is constant, that will give us the streamline, and that constant gives me implies y is equal to x tan alpha, and once y is equal to x tan alpha, if I draw a line, and here this makes an angle alpha, this is the way the fluid will flow, all these angles are alpha. So, this is a uniform flow which subtends an angle alpha with the x axis, and this is the way. And if you look at again here what will happen to q, it can be easily find that speed is also that same as u naught. So, here also, so we call this as a, this example we call this uniform flow. This is also a situation of a uniform flow which is making an angle r, which makes an angle alpha with the x axis. So, this is horizontal, whereas in this case this is making an angle alpha with the x axis. So, these examples suggest us that we can always find several situations where our flow is by using the complex function theory, we can represent the flow characteristics or represent various flow, describe various flows. Now, there are some flows which are very important. So, I will come to few more cases. Let us look at a very important thing in marine hydrodynamics is source and sink. What is a source and what is a sink? In physical terminology, always we understand A source is something from here, something we say source means there is something which from where the things will be out, and if you say sink, as if something is entering there. So, in this same manner, if in a fluid flow, in a particularly in a two dimensional fluid flow, a slope consists of a point from where the liquid will emerge out, and in the it will emerge in the symmetrical in the radial direction out. Sorry, it will go through from the point source, and it will symmetrically will come out in the radial direction, and then this point we call this as a this point we call this simple source. Again, if I will say if 2 pi m is the rate of emission of volume per unit time, then we say m as the strength of the source. M as the strength of the source. And if I say if let u r be the radial component of velocity, because here the fluid flows in the radial direction, there is no flow in the tangential direction. So, what will happen, the total the flux out of the total flux which total flux, if I consider which comes out of the circle of radius r, let me look at a circle, because fluid is emerging out. If I look at this, how much total fluid that will be emerging out, that the total flux will give me 2 pi r into u r, because I am considering a two dimensional flow, and that will be same as the total rate of the total emission, that is 2 pi into m. If I equate both the things, and my u r will be m by r, and what is u r? This is nothing but phi r, because this is the radial component of velocity, this is m by r, which gives me phi is equal to m log r plus f of theta, where f of theta is arbitrary function of a. Now, again we know that r del phi by del r is equal to L psi by del theta, because the velocity potential and the streamlines, they are related in the cylindrical polar coordinate, when x is r cos theta, y is r sin theta, then if I is the velocity potential and psi is the stream function, then r del phi by del r is del psi by del theta, and if I substitute for phi, that gives me del psi by del theta is equal to m, and that gives psi is equal to m theta plus g of r. Now, so what will happen, my phi plus psi, so w I can easily get, that is phi plus I psi, and it can be easily said again using r del phi by del r is del psi by del theta, that will if I utilize this characteristics, my g theta is 0 and my f theta is 0 and gr is 0, and that will give me phi plus w is phi plus I psi, that will give me m log r plus I m theta, and that will give me, if I put it m into log r e to the power I theta, and which I can write as m log z. So, if I have a source of strength m, then my complex velocity potential is w is m log z. Now, some of the characteristics of the source is that u r, we have seen that u r is m by r as r tends to infinity, u r is 0. So, that means source at large distance the velocity, radial component of velocity is 0, whereas no tangential component of velocity in this case. That means there is a no flow only in the local distance, local region there will be a fluid which is emerging out, but when it goes to far field there is no such flow. And again I will just say, if this is when the source is z is at 0. Now, if I say the point the source is at z is equal to z naught, then my w will be m log z minus z naught. I am just shifting the origin. So, this becomes the complex velocity potential if the source is at z is equal to z naught. Another point here I want to mention, a sink in the same line, a sink is nothing but is a negative source, means that in a sink the fluid, in case of a source the fluid goes out, where in case of a sink the fluid will emerge to a particular point from all direction, in the radial direction it will, if I just say the fluid in all direction it will come to this point. Sorry, this is, and this point becomes a sink, and so it is often called a sink as a negative source. In fact, in many potential flow problems this source and sink concept is used very much, and particularly when you look at the fundamental singularity in a flow problem, particularly if you look at the potential flow problems, and sometimes these sources or sinks are called the fundamental singularity in a potential flow problem. And I will stop here. In the next class we will again discuss various problems in the presence of sources and sinks and other singularity, or in the presence of boundaries, again using the same complex function theory approach, basically the complex velocity potential. With this I will stop today. Thank you.